Jai Hind everyone, I am Deepak Narang, Assistant Professor in EN Department of Ajay Kumar Garg Engineering College. The topic of my today's talk is frequency domain analysis. So in this we are basically going to discuss these specifications, that is transfer function, resonant frequency, resonant peak, bandwidth, and what are various plots which are being used in frequency response analysis in frequency domain. Okay. So starting with the introduction, what exactly is frequency domain analysis or frequency response? In this, basically we apply sinusoidal signal to the input as input to LTI linear system, and then it produces a steady state output which is also sinusoidal in nature. Hence, the input and output sinusoidal signal have the same frequency but the different amplitude and phase angles. So, if we represent our input as function of sinusoidal, that is A sin omega t, so then the output can be represented as A sin omega t plus phi. So, where A is magnitude, this phi is phase. So this magnitude and phase relationship between sinusoidal input and steady state output is termed as frequency response. And in frequency domain, we replace S by j omega. So we represent open loop transfer function Js is equal to Gj omega. So we can write in frequency domain, Gj omega is at combination of magnitude and its phase, that is mode of Gj omega and angle of Gj omega. So at omega is equal to omega naught, we will replace omega by omega naught. Okay. So the output signal becomes Ct is equal to A Gj omega sin omega naught t plus phase. As we know, Ct is equal to A sin omega t plus phi. Okay. So this magnitude is obtained by multiplying A with amplitude of output sinusoidal signal is obtained by multiplying the amplitude of input signal and the magnitude of Gj omega at omega is equal to omega naught. Same way, the phase of output signal is obtained by adding the phase of input, this is input, and plus sinusoidal and the phase of Gj omega at omega is equal to omega naught at omega is equal to omega naught. So, these are various frequency domain specifications. First is resonant peak. This is the maximum value of closed loop transfer function. Resonant frequency, the frequency at which resonant peak occurs. For example, if this is our response, okay, we can see here we are having the maximum value. So this is our maximum resonant peak, okay, and this is occurring at this frequency, and this is termed as resonant frequency. And next is bandwidth. The range of frequency for the system normalized gain is more than minus 3 dB, or we can say the range of frequency through which the signals in control system are being passed, and after this frequency, cutoff frequency, the signals are blocked. Cutoff rate, it is the slope of the log magnitude curve near the cutoff frequency. Gain margin, the value of gain to be added to a system in order to bring the system to the verge of stability. For example, if this is frequency response of any system and it is having this value as a intersecting value, this is our critical point -1 plus j 0. So here this gap is termed as gain margin. So 1 by A is equal to gain margin. Okay, it means if we multiply the system gain by 1 by A, then the response will approach this point and the system will it will bring the system to the verge of instability. In the same manner, phase margin is additional phase lag to be added at the gain crossover frequency in order to bring the system to the verge of instability. Now, what is phase crossover frequency? The frequency at which the phase of open loop transfer function is 180 degree, like this. Here, this frequency is termed as phase crossover frequency because at this frequency the phase of this system is -180 degree. And the gain crossover frequency, it is the frequency at which the magnitude of open loop transfer function is unity. If this is unit circle and response is cutting at this frequency, here the magnitude is 1. So this frequency termed as gain crossover frequency. Now let us derive this specification in frequency domain. This is the standard transfer function for second order closed loop system as we use in time domain. Okay, so replace here S by j omega. So we get Ts is equal to, T j omega is equal to omega n square upon j omega square plus 2 zeta omega n j omega plus omega n square. This is equal to omega n square upon minus omega square plus 2 zeta omega n into j omega plus omega n square. Taking omega n square common, so we'll get 1 upon 1 minus 1 upon 1 minus omega upon omega n whole square plus 2 zeta omega upon omega n j. Replacing omega by omega n is equal to u, which is our normalized frequency. So this is equal to 1 upon 1 minus u square plus 2 zeta u of j. Okay, so we converted our transfer function which was given in time domain into frequency domain by replacing s into j omega. From here we can find our magnitude is equal to 1 minus u square plus 2 zeta u square, as magnitude is equal to real square plus imaginary square, and likewise phase is equal to minus tan inverse imaginary part over real part, which comes out equal to minus of tangent inverse 2 zeta omega n upon 1 minus u square. So we shall use, so we have obtained magnitude and phase in frequency domain like this. Now we are going to use this term for obtaining many specifications. So we'll use this as for next to find resonant frequency. As we know, the resonant frequency is that frequency where the magnitude of the frequency response has the maximum peak, and as we know, if this is the frequency response, here will exist resonant frequency because this is the maximum value of this response. And at this we know, at omega is equal to omega r, the slope of response is equal to 0, and we know we have obtained m is equal to 1 minus u square plus 2 zeta like this. So if we take the slope by derivating of this magnitude with respect to normalized frequency, we get minus 1 by 2 1 minus u square whole square plus 2 zeta u whole square raised to power 3 by 2, and here we will get 2 1 minus u square minus 2u plus this is 8 zeta square into u. Okay, so this is equal to 0 at u is equal to u r. At resonant frequency, this slope is 0. That is why we are putting this slope equation is equal to 0. This implies that 2 1 minus u r, we are replacing u by u r because we are putting this equation is equal to 0 because we are operating at now resonant frequency. This will become minus 4u plus 8 zeta square u is equal to 0. By taking 4u common, we get u r square minus 1 plus 2 zeta square is equal to 0, and we get u r is equal to 1 minus 2 zeta square, and we get our resonant frequency, normalized resonant frequency is equal to 1 minus 2 zeta square, and we know u r is nothing but the normalized frequency, that is omega r upon omega n. We get omega r is equal to omega n 1 minus 2 zeta square. So this is the value of resonant frequency. This is the value of resonant frequency. Okay. Now next is resonant peak. So how to obtain resonant peak? Obviously this is the magnitude, maximum magnitude at this frequency. As we know, m is equal to 1 upon 1 minus u square whole square plus 2 zeta u whole square, and we have obtained So at resonant frequency, this will be represented as MR is equal to 1 minus UR square plus 2 zeta UR square, and we have obtained UR is equal to 1 minus 2 zeta square. Okay, so by putting this value into this equation, we get 1 upon 1 minus 1 plus 2 zeta square plus 4 zeta square 1 minus 2 zeta square, and into this we will get this is equal to 1 upon 4 zeta raised to power 4 plus 4 zeta square minus 8 zeta raised to power 4. By taking 4 zeta square common from this part, this can be written as 4 zeta square minus 4. So this can be written as 1 upon 2 zeta 1 minus zeta square. Okay, so this is the value of our maximum resonant peak. Okay, so we have obtained these values, resonant peak and resonant frequency. We can conclude, we can have several cases from these two equations. If damping is equal to 0, that is if zeta is equal to 0, it means if this is equal to 0, our resonant frequency will be equal to this, will be equal to its natural frequency, and in that case this magnitude will approach to infinity. Okay, and second case is if damping is less than 1 by root 2, in such case our resonant frequency will be less than natural frequency and MR has value greater than 1. Like in this graph we can see here at this particular frequency the response is greater than 1, magnitude 1. It means system is having overshoot, because here damping is less than 1 by root 2, and if damping is greater than 1 by root 2, the slope of magnitude decreases monotonically at magnitude is equal to 1 and frequency is equal to 0, and we can say it continues to decrease and reaches to minimum value. This is the case when damping is greater than 1 by root 2. Okay, and the phase value at resonant frequency is at this point is minus 90 degree. Next is cutoff frequency. It is the frequency at which this magnitude has a value of 0.707 of its normal value, and the signal above this cutoff frequency is attenuated in passing through a system. And for the feedback control system, the range of frequencies over which magnitude is equal or greater than 1 by root 2 is defined as its band width. Like here this is 1 by root 2 of its nominal value. After this the signals will get attenuated. and up to this range of frequency will be termed as its bandwidth. Okay, so we can write our magnitude is equal to 1 minus UB square whole square plus 2 zeta. This is equal to 1 upon root 2. Okay, 1 by root 2 of its nominal value, and its nominal value is here 1. So that is why it is equal to 1 by root 2. Okay, by squaring both sides, we get 2 is equal to 1 minus UB square whole square plus 2 zeta UB square, and if we open this equation, 1 plus and we get 0 is equal to UB4 minus 2 UB square 1 minus 2 zeta square and minus 1, this is equal to 0. Okay, so let UB square is equal to x. So this becomes a second order equation. Okay, by using the formula that x is equal to minus b plus minus b square minus 4ac upon 2a, where b is our this factor, a is 1, c is 1. So we get bandwidth or range of frequencies. Okay, this is equal to like this. Okay, by putting these values into this second order quadratic equation. So this is the value of cutoff frequency. So we can comment over on the basis of this specification, we can comment over time and frequency domain correlation, because in time domain we get the specification like rise time, peak time, maximum peak overshoot and settling time. Okay, these are specification which we obtained in time domain. In frequency domain we obtained resonant frequency, resonant peak, bandwidth. Okay, so this is resonant frequency in case of frequency domain, this is damped oscillation frequency in case of time domain, this is resonant peak in case of frequency domain, this is peak overshoot value in case of time domain. And we observe that both these values are function of damping. In both the values we are getting zeta, and for perfect operation this MP should have 10 to 15% value, and this resonant peak should be settled around 1 to 1.4. And as the damping increases, if damping is increases, this peak overshoot gets down and get vanished at damping is equal to 1. Likewise in frequency domain, this resonant peak also vanishes, but at damping is equal to 1 by root 2. If damping is equal to 0, the peak overshoot achieves 100%, and likewise here resonant peak goes to infinity, which is undesirable condition. Bandwidth and rise time are inversely proportional to each other, that is, if bandwidth is increasing, it means it decreases the rise time. So these are some frequency response plots which we use for stability analysis in frequency domain: Bode plot, polar plot, Nichols plot, M and N circles. What are advantages of being using frequency domain analysis. First of all, transfer function which are complicated to determine the behavior of experimentally can be determined using frequency domain analysis. Design of system and adjusting the parameter of system can be easily carried out. Corrective measurement of noise disturbance which is generated in the system can easily be determined using the frequency domain analysis. Absolute and relative stability of closed loop system can also be estimated from the knowledge of open loop frequency domain analysis. This is also applicable to non-linear control system. Let us consider one example which states a system of third order shows resonant peak of 2, that is MR is given equal to 2. Resonant frequency is, that is omega r is equal to 3 radian per second. Okay, then find the time domain specification, that is rise time, peak time and settling time. Okay, MR is equal to 2, omega r is equal to 3. So we put formula of MR is equal to 1 upon 2 zeta square root 1 minus this is equal to 2. So by this we get our zeta comes out equal to this. Okay, from this we can obtain resonant frequency, as resonant frequency is equal to omega r omega n into 1 minus 2 zeta square. Zeta we have already obtained in previous step, and through this we can get omega r, and omega r is given which is equal to 3. We can basically obtain our omega n from this equation which is coming out 3.223 radian per second. And by putting value of omega n into the second order transfer function, we get the transfer function like this, and through here we can easily obtain our rise time, okay, which is equal to pi minus theta upon omega d, and theta is equal to tangent inverse square root of 1 minus zeta square upon zeta, and we get theta is equal to 1.3 radians. Okay, damped oscillation is equal to omega d omega n into 1 minus zeta square. Zeta we know, omega n we know, we can easily obtain frequency of damped oscillation in time domain. Okay, so we can calculate all the values. We know the pi, omega d, we know omega n, we know zeta. So by putting these values into their respective formulas, we can get all the values. And second problem state, a second order system has overshoot of, that is MP is given 50%. Okay, and period of oscillation is 0.2 second. Now this is period of oscillation, that is t is given 0.2. Now first of all, MP as we know, this is equal to e raised to power minus zeta pi over 1 minus zeta square. Zeta is, MP is given to us, that is 50 upon 100 is equal to e raised to power minus zeta pi over 1 minus zeta square. Taking natural log both the side, okay, we can get value of zeta which is coming out 0.2154. Now period of oscillation is given, and we know t is equal to, frequency is equal to 1 upon t. From here we can get the frequency which comes out 5 Hz, and omega d will be equal to 2 pi into fd. So here we can get the omega d, and omega d is equal to omega n into 1 minus zeta square. Okay, so we can calculate omega n, this is coming out 32.16. Now we know omega n, we know zeta, and we can get resonant peak and resonant frequency. Okay, so this was all about today's talk. This is my book for this particular topic. Thank you. Jai Hind.